got here? Joey claimed he would be here. Okay. Layla. Ethan. Trent. Not you, is it? And then I'm missing every single one of my BDs. All right. Kevin's not here either. Man. Okay. This kind of sucks, but it's too bad. Does everybody have a calculator? Does everybody have a calculator? Does anyone need to borrow a calculator? You need to borrow. Okay. Boom, boom, boom. So if there's no questions from anything, maybe, okay, so maybe before I jump into this, I'll ask myself a question. Hey Jeff, can you run down what we've done so far? Oh, okay. Also, before I get too far, we desperately need to have a quiz, and I don't think I've announced one yet, have I? No. Okay. We need a quiz in our lives, so let's have a quiz on, let's say 5.2. Let me look at what these objects, these ideas are. Yeah. 5.2, 5.3. So that would be like just the basics of power functions and behavior kind of stuff, yes? 5.3 is multiplicities, finding the roots, so forth, yes? So we'll have a 5.2, 5.3 quiz on, we could do it tomorrow, but you guys want it, let's make it Thursday. And then we'll have a quiz on 5.4, 5.5. We'll make that next Wednesday. I like it. Now everybody should be, I would say in the homework you should be like at least in 5.3, if not in 5.4, somewhere in there. Yes? If you're ahead of that, fantastic. If you're behind that, rub. So you should totally be ready for this Thursday's 5.2, 5.3 quiz. You should be able to do all the homework. And then you got next Tuesday to ask questions before the quiz on Wednesday. And this is like synthetic and long division, yes? Synthetic and long division. And this was, you could do it, Jeff. Can you do it? Oh yeah, so that was the actually using synthetic and long to find zeros for polynomial functions. This one. I just had a few people with questions from this section. So this is finding all the solutions using synthetic division, right? Factoring something all the way down using synthetic division. Okay, I love it. So 2 quizzes in our relatively near future, which is good. You want more grades, so you're welcome. Anything from homework stuff before I do this thing? Okay. So just kind of review what this is all about. This is about power functions and end behavior. If I ask you for the end behavior, and I remember talking about pre-calc students about this, but if you go into the Math Science Center or the CISL for help, they might explain end behavior differently. Have I addressed that in here yet? I did? All right, good. I always need external memory help. Okay. So if I see something like that, I'm being a little evil, so be careful. What determines the end behavior of this polynomial? Highest degree? And what's the highest degree term?
4.
Fourth degree? And so, but what else is here that's important? The fact that it's, what is it about a parabola that we want to know?
Oh, which direction it's going? Yeah.
Yeah, so this opens.
Down.
All right, so what is the way I need you to tell me the end behavior? Do you have to tell me as x goes to infinity, y goes to? I always hate that. I think this is the worst place to put that. All you need to do for me, for end behavior, this is why the end behavior is what it is. It goes like negative x to the fourth degree negative, and of course, like you just said, on the ends it's going to look like a down parabola. Yes? That is it. That's all you got to show me. Once we get into 5-6, I'm going to show you some better notation to address what happens to a function if we let x get big or blah, blah, blah. There's better notation that's going to lead into calculus. The notation the book uses and other people use for this is silly to me. It just makes it more clouded. I want my notation to make things clearer. Okay. So if you go for help, always be ready to show them notes, examples we've done, and say, this is how my teacher showed us to do this, right? And they can say whatever the hell they want to about me, because they have the right to be wrong, but this is the way I want you to do it. So that's 5-2. 5-3, of course, got into a synthetic division, long division, right? I think we're all cool with synthetic. Is this true? Especially the way we do it. If I do a long division first, and then I show you the beauty of the synthetic division, you're like, okay, I can deal with that. Give me that. Okay. 5-4 and 5-5, they together sort of get into the making the list of possible rational roots and then checking them, right? And then you had the lower bounds, upper bounds, you had Descartes' rule of signs. Are you guys at all with me? No? Is anybody with me? So let me see, do I have a copy of that here? No. Okay, darn it. Back to my off. Okay, so there was a worksheet we went over, and here we go. Perfect. Yes, this guy. Descartes' rule of signs. This is kind of like the truncated version. There's more to it than this, but this is what I thought was most immediately important. Upper bounds, lower bounds. These are all just ways to shrink the size of the list of numbers you have to check. So you make the list of numbers, and those are all numbers that might work, and then you have to try them. And of course, I try to show you there are several ways that might shrink that list, which would decrease the amount of work you have to do. So everybody's semi with me. I can't stress enough how important factoring is no matter where you go from here. Factoring is very often the name of the game. You might factor after you do some other weird shit, but factoring almost always shows up at some point in a problem. So synthetic division just drastically increases the number of things we can factor. It's crazy. Okay. If you need one of these, I've got more. If you don't think you got this from me, you can tell me, and I can give it to you. Okay. Yes. Okay. Oh. Okay. Okay. All right. Who was here today? Oh wait. Oh yeah.
Yeah. Would you say that this paper is more so 5.4 or 5.5?
Oh, what do you think? I think, I think 5.4 is where this is introduced, and 5.5 is where they use it. Let me double check. I almost don't care what you think, what people think about this. I know stuff. I don't necessarily know where it's in the book. But let me see. Yeah, this was specifically about just synthetic and long division by itself. And then 5.5 was creating a list of things and using synthetic to get it. Is that cool? So 5.4 just said, hey, these things exist. And then 5.5 said, hey, those things exist. We could use them to help in what we're doing. So 5455 introduced long and synthetic. 54 introduced long and synthetic. 55 said, hey, we can use that shit. We can factor stuff and see the multiplicities and all that kind of business. Okay. I like it. My BD's game. Hey. Anything else from homework stuff? And if anybody else needs one, I got one more of these basically. If anybody else needs one of these sheets. Okay. All right. If you weren't here earlier, we got 2 quizzes coming up. One's Thursday, one's next Wednesday. Okay. And oh yeah. Kevin's not here. Which this your and then I can put it in here. Yes. Cool. All right, so let's do this. Yes. Let's see. Yeah, I'm not gonna make one up out of nowhere that works the way I want it to. How did I tell if something is a upper bound? I'm given a polynomial. Let's say it's ax to the n plus blah blah blah. How do I tell if something is an upper bound? What process would I go through to show that something is an upper bound? So like, if this one had, if at the end it had plus 8, and let's say the first number was 3, yes? How do you create the list of, let's start here. How do you create the list of possible rational roots?
The constant, right?
Do it again, yeah. So on the top goes all the factors of this guy. And of course, bless you. What else do I do? Factors of 3, okay. All right, now listen. We discussed why this makes sense. I told you why this procedure makes sense. I showed you concrete examples that lead to fractions, and we saw where the parts came from. You guys with me? We do that, and then we develop a process. Okay. But it's okay if right now you forgot why this is true. I'd much rather, I need you to understand why this makes sense instead of just memorizing it. Now you could just memorize it. I don't need this plus and minus, by the way. And of course here I would make the ratios, right? So I get 1, 2, 4, 8, 1/3, 2/3, 4/3, 8/3. Right? But why does this make sense? If I have a 3 there and an 8 there, couldn't part of it have been this? And couldn't part of it have been this? And then maybe the last part could have been, yeah, sure, it'd be 3 2s. That'll be okay. Could it be this? Wouldn't that give me 3x cubed? And wouldn't this give me 8? You guys see that? What's the zeros there? What 0 comes from this? What makes that 0?
2/3.
2/3. 2 is on the top. 3 is on the bottom. 2 is on the top. 3 is on the bottom. Now, real quick, I'll tell you what. Forget these are here. What else could have been here? Considering there's an 8 at the end, what else could have been here? Sure, it's negative already. What else could have been here, though? All right. How far back do I need to go? Let me see. The only way I can make the last term 8 is if all the numbers at the end are factors of 8. Does that make sense? Yeah. Same way that we can tell what the end behavior is going to be. If it's already factored, because I can just put together the x's again. I can just put them back together. So, for example, if I had this, again, okay. Okay. Can anyone tell me if I did multiply this out? Dear God, don't. If I did multiply this out, what would the first term be? What would the first term be from just that piece if I multiply it out? 28 squared. Now, if I took that, 28 squared plus other shit, yes? I don't care about the other shit. I'm just looking at the first term, correct? So that'll be 20x squared times x. So far I got 20x cubed. Plus other shit. 20x cubed times x. Plus other shit, yes? So what do I get? 20x to the 4th power. Okay, so the first term would be 20x to the 4th. So therefore, all the numbers that show up at the front have to be factors of that number. Yes? All right, right there. Is everybody with me? Right there. That's just a known fact. Whatever number is in the front, the factors of it are what goes in the fronts of all the pieces of it. Okay. Because when I put them back together, I get that. What do I get at the end? I get other terms. Blah, 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 blah. What's my constant term going to be? What's this number at the end going to be? Well, how did I get the number at the front? I just looked at all the fronts, yes? Okay, let's do this. Let's multiply this out. Let me make one that's not quite as crazy. Okay. We're going to FOIL this out. So if I FOIL this out, I'm going to get 6x squared. What's this? Minus 8x. Plus 3x. Minus 4. Okay. And then I'm going to get 6x cubed. Plus 18x squared. I'll do this whole minus 5x squared. Minus 15x. Minus 4x. Minus 12. So then I get 6x cubed plus 13x squared minus 19x plus 12. Okay, so all of you guys could do that. That's just brute force. You guys could multiply, 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 and then combine, right? You guys could do that all day. You want me to give this wrong because it's just, you can sink your teeth. You just multiply. Where'd the first number come from? Where'd it come from? Where'd the first number come from? 2 times 3 times 1, yes? Where'd the last number come from? 1 times negative 4 times 3, yes? All right, this is exactly why what we do works. This is exactly why what we do works. Whatever the first number is, okay. And let's go one step further. So all the ends have to be factors of this, and all the beginnings have to be factors of this, yes? Now let's see how that ties into the zeros. Can anyone tell me the zeros of this? What comes from here? What zero does this give me here? What makes this 0? No, negative 1
Negative 1.
half. If you subtract 1, divide by 2, right? Make it equal to 0. Subtract 1, divide by 2. So negative 1 half. What else is a 0? Add 4, divide by 3. So 4/3. What else is a 0? Negative 3. And I'll put it over 1 just so it looks like the other guys. Yes, so they're not suspicious of them. I'll put them in stealth. He's in disguise. Where did the numbers on the bottom come from? Which factors of 6? Where did the numbers on the top come from? Factors of 20. That's exactly why we do what we do. That's exactly why I know this is what's going to happen. So when I'm given a problem like this problem, first number's a 3, last number's 8. The top is going to be factors of 8. The bottom is going to be factors of 3. The question is just which combination of those works, and that's why we have to like plug them all in, try synthetic division until we get one that works. But of course it makes sense. I'm going to start with a list of everything that could work. Because I'm not just going to plug every damn number in existence in. I want just the numbers that could work. So like, could 11 work for this? Of course not, because it's not a factor of 8. So that'd be silly to try 11, right? It'd be silly to try 5. So that's why we make a list. I want to know what's all the stuff I need to try. And then the next level we went into was, dear God, Jeff, is there any way to cut the size of, have you seen the size of these lists? Dear God, Jeff, can you please cut them down? And I showed you 2 things really. The idea of bounds, upper, lower, and the idea of the Descartes rule of size, right? Delusional, sick little Descartes laying on his bed watching the fly, right? I told you guys about that, right? That's, if I didn't, you're all like, what the hell's it? Okay, so, if we took this, now that you helped me create something that works. All right, if we take this, how do I make the list of possible rational zeros? Here, I'll use an E sometimes. Possible rational zeros.
Factors of 12.
Good. Factors of 12. Go up top. And on the bottom goes.
1, 2, 6.
What's up, sorry?
1, 2, 3, 6.
Yeah, factors of the first guy. I don't need plus minus. Okay. So this is going to come out to be kind of big. Do you guys get that? I've got whole numbers because I divide by 1. So I get all the whole numbers when I divide by 1, divide by 1, divide by 1. Then I divide by 2, and I pick up a fraction there, pick up a fraction there, and the other ones reduce to whole numbers. I already got those. Then I move on to, let's see, does anybody else work? 4. 3's good. I got 3 already. 4 would be 4/3. 4/6 2/3. I don't know why I don't have. Oh yeah, because I skipped it, Jeff. Good job, buddy. 2/3, 4/3, 1/3. So I'm looking at the 3. There we go. And then if I try the 6, I get 1/6, 2/6 I've got, 3/6 I've got, 4/6 I've got, 6/6 I got. Okay. That's long. These are all the possible rational numbers that will divide evenly into this. So everybody with me? So of course it makes sense. I want to do that first because now I know what I have to try. Does Descartes help us out at all here? What do I mean by that? Does Descartes help us? And you're all like, is there a guy that comes in sometimes that helps us? Someone knows, Christine? Who's this Descartes guy? Does Descartes help us? What's Descartes say right now? Given G of X, what can I see? Are they all the same sign? No. So I don't, they have more than 0 possible positive roots, yes? Do the signs alternate? No, so they have more than 0 possible negative roots. So Descartes doesn't help me here. Yes? Yes?
Can you explain the card?
Yeah. So just to remind you, I basically just said it, but it's also on that sheet that I don't know what I've done with now, but just to show you, I don't know what I did. Descartes says, if I have a polynomial and the sign does not change at all, there are no positive roots. And if I have a polynomial where the sign does nothing but change, then there's no negative roots. There's actually more to it than this, but this is the most immediately useful thing that comes from his rule. You guys with me? It's on that one handout that I gave you. Okay.
Could you also quickly refresh on like upper and lower bound?
Yeah, that's what I'm working towards.
Okay.
Now, I am not sure if this is going to work, but we'll try it. If not, I'll just remind you what's supposed to happen. What I normally do, if I have this big ass list of things, I try to pick a number that's sort of in the middle. So I'm gonna pick positive 4, and let's see what happens. So I'm dividing by a positive, right? Remind me what 4 relates to. What factor would 4 relate to? He's in a little penalty box. What does he relate to? X minus 4, right? So if it goes in evenly, I know that x minus 4 is a factor. So let's try this out. 6 comes down, then what? Yeah, 24, 37. 37 times 4 is, I believe, 148. 148 minus 19 is 129. 120 times 4 is big positive, and this is positive. So was the result all the same sign? That means, so when I divide by a positive number, and I get all the same sign in my answer, that's an upper bound. What does upper bound mean?
It means that number in any hierarchy.
Yeah, I know 4 doesn't work because it didn't have a 0. But by itself, it just means no number above 4 can work. So what numbers can I throw out of my list? 4, positive 4, right?
4, 6.
Positive 6, positive 12. I can throw all those out, yes? So in this one thing, I just threw out, 3 things. Well, that's good. I got 3 for 1. That's pretty good. What if I divide by negative 4? I don't know if this is going to work. Let's see. I feel like it might not. Have some faith, Jeff. I don't know. 6, negative 24. So far, so good. 44, yes. And then this will be 25. 25 to negative 100. Okay, so I divided by a negative number, yes? You're all like, yes, Jeff. We just saw you do it. It's right here. Was my result only changing sign?
Yeah.
Okay, so do you see how it relates to the Descartes rule of signs? If they're all the same sign, there's no positive roots. If they're all always changing sign, there's no negatives. If I divide by a positive number and they stay the same sign, that's an upper bound. If I divide by a negative number and they only change signs, that's a lower bound. So now I know not only can I throw out positive 4, positive 6, I can also throw out negative 4, negative 6, negative 12. So now my new list would be 1, 2, 3, 1/2, 3/2, 4/3, 2/3, 1/3, 1/6. Still long, I agree with you. So I mean, I wouldn't give you this one necessarily. But it's a lot shorter than it was. Now maybe 3 would have worked. Maybe 3 was a bound, yes? But when I have a problem like this, I normally try to do a number that's sort of in the middle so that I have a higher chance to see if it's a bound, yes? I don't know if that makes any sense to you guys. Now, I could get lucky. Maybe 1 is a bound, and then it throws out a lot of shit. I don't know. But it's up to you how much you want to gamble. What I normally do in a test, since we only have so much time, is I try to make it a problem that Descartes will cut in half, and then I have you do a problem to show that you found an upper or a lower bound. And then that chops out a bunch of other numbers. And then maybe you have like 3 left to try. You guys see? So if you're unlucky and you get on the last try, at least you only had 3 to try. Does that make any sense? A little bit, okay. Okay, how are we doing? How's that? Okay. All right, some of you guys are looking at me like this. But you're not saying anything, so I don't know what to do with that expression, except talk about it like I just did. Okay. We can always go deeper into an idea if it doesn't make sense. There's no problem with that. In fact, some might argue that's my whole job. Okay. Yes, go ahead.
Can we do another one?
Sure. I laugh because these are not like easy to make up on the spot, but if you give me a moment, if everybody will just give me a moment, I'll make up one that Descartes will actually help us with. Does that sound nice? That sounds nice. Jeff, that sounds nice. Do that. I will. Oh shit. Okay, this is gonna be exciting. Everybody just remain calm. No, Jeff. There you go. Okay. How was class today, honey? Well, he just sat there writing stuff for himself. Oh, sounds great. Let's see. I might as well just be careful about this. Oh boy, this is, ooh, I like this. This is nice and gross. Okay, let's see. Oh my God. Okay, let me see. Let me write this down and then double check here. Look at that. That's beautiful. Didn't work. Damn it. Let's see. Yeah, looks good there. That's fine. So then what happened, Jeff? Can you just not add 12x cubed, 7x cubed? Okay. 18, 42, and 5 is 65. 63 and 30 is 93 and 45. So what the hell? All right, I don't see 2, 19, 65, 93, 45. Yeah. Okay. Is that what it was? Let's see. Oh, that's what it was. Oh. How you guys doing out there? We're fine, Jeff. This is great. Oh yeah, that'll work. Okay, here we go. There it is, in all of its glory. Yes? Sorry, it just took a second. Can you guys take a moment and create the list of possible rational roots? And if you can't, that's a great time to ask questions. Yes? Sorry? Let me see. Any more Oh, this one's written on a little bit, but it's okay. So, what are you guys putting on the top here?
Positive all factors of 45.
5, 9, 45.
Good. And then on the bottom just goes, I don't need that plus or minus. 1 and 2, yes? For factors of 2. And then, of course, you're going to get, the list will be 1, 3, 5, 9, plus or minus 1, 3, 5, 9, 15, 45, and then divided by 2. 1 half, 3 halves, 5 halves, 9 halves, 15 halves, 45 halves. All right. That's great, Jeff. Looks good. Thanks, man. What does Descartes say about this situation? What does Descartes say? And are you guys ready for something fascinating? Right now, we're not taking a quiz. We're not doing any of that. You could actually look at the worksheet I gave you. You could look at the book. You know what I mean? You should try to force yourself to remember, because you're going to have to be tested on this. You're not going to have stuff to look at. But right now, that's fine. So, what does Descartes say about this polynomial? Yeah, it's all positive, so therefore, there's no, it's all positive, so there's no positive roots. Now, I'm pretty sure I talked to you about why that makes sense. If I put a positive number, if I put any positive number in here, is it possible for it to come out to be 0? I think about it for a second. Think about it. If I put a positive number in, what's true about every term? I don't care what positive number you put in here. What's true about every single term? They will all be positive, yes? No matter what positive number you put in, does everyone agree every term will be positive? Is there any way you could add a bunch of positive numbers and have the answer be 0? No. If you can, you probably want to get help balancing your check. It's not a good situation. You guys come with me. You guys see that? That's why this makes sense, because there's no way a positive number can make it 0. If one of them was negative, then it could work, because at least part of it's subtracting from itself. Then there could be a positive number that makes the answer 0, because part of it is subtracting, so maybe it does cancel. Nothing here would cancel. Now, if I put in a negative number, does anyone know what sign this would be? If I put in any negative number, what sign would this number be? What happens negative to a 4th power? What happens? It comes out positive. So this number would be positive. If I put a negative number in, this number would be?
Negative.
Yeah, so 4 negatives, 2 cancel, the answer is positive. 3 negatives, 2 cancel, the answer is negative. So if I have an even number of negatives, the answer is positive. If I have an odd number of negatives, the answer is negative. So why will negative roots work? Because that's positive, negative, positive, negative, positive. Those could cancel out. So that's why there could be some negative answers. But there can't be any positive answers, because if I put a positive, nothing cancels out. There's no way to make it 0. Okay. Yes?
So even amount of positive roots are positive, or is it negative amount of roots?
No. Okay, so if I have, I need paper. If I have I have an even number of negative numbers, right? How many negatives do you see? 4. So the answer, will it be negative or positive? Will the answer be negative or positive? Because what do every 2 negatives do? every two negatives cancel, correct? So if I have an even number of negatives, everybody can pair up and cancel, yes? If I have an odd number of negatives, there's always going to be an odd guy out. He's going to be left alive at the end. All the other ones get together and kill each other. He's like, what just happened? Okay, maybe. Maybe. This is some good shit to know. So if I said what's negative 1 to the 708th power, what's that? Say again? What is it? What is it exactly? Sure, it's positive. What is it though? 1. Yeah, because there's an even number of negatives. So the answer's positive, and 1 times 1 is 1, correct? Okay, I like it. So coming back to this guy. What does Descartes' rule of signs say? There's no, what now? No positive roots. So what can I do with my list? What can I throw out? All the positive roots, so I only have negative ones. So I just cut my list in half. It's still pretty big, but it's half as big as it used to be. Yes? Now, who feels like a gambler? What number do you want to try? Maybe it's a lower bound. If we find a lower bound, we can cut our list even more.
9.
Go ahead and try negative 5. Try to divide by negative 5. Where did I make this? There it is. So really quickly, you can see very quickly that it's not going to be a bound. Do you guys see? If I bring this 2 down, 2 times negative 5 is? Negative 10. 19 minus 10 is? 9. Now, already, I know it's not going to be a lower bound. Already I do. Why? How do I already know it's not going to be a lower bound? What do the signs of the things have to do if it's going to be a lower bound? They have to change constantly, and already I got 2 next to each other that are positive. Now I can keep going because maybe it's actually an answer, but I know it's not going to be a bound. Negative 45, 20, negative 100, negative 7, and then 35 makes 80. So it didn't go in. Poor little dude. So I will say this, there's one fractional answer, and there's a number that works twice. So now listen, I gotta remind you, so if I make a problem on the test, I'll make it ahead of time, I'll make it work a certain way, so that the list becomes small. Our list is still pretty big, and we didn't find it bound yet. It's extra hard to make an example problem where you get a number that's a nice bound. Maybe 9. I think I heard somebody say 9. Did anyone try 9? Negative 9. I mean, we only try negative numbers. Did you try negative 9? It could be about. I don't know. We could try. Okay. Does everyone? I need you. There's 2 levels of thing here. There's, oh my God, this would take forever. But again, when did I make this problem? Just now. So I didn't have any time to make it like work a certain way. Do you know what I mean? I just made it work, period. Yes? So there are things that will work. So we have 2 levels of stuff. Do you understand what to try? And do you understand I will make the problem so you don't have a billion things to try? Right? Do you understand the steps? And also, internalize that I'm not going to let the list be this big. So, because I need to be able to tell the difference between somebody out here looking like this because there's a lot of shit to try versus somebody looking like that because they don't know what I'm doing, right? I need to know the difference. So you're not going to have this on your own, this big ass list, and you're just like, oh God, here we go, hopefully I get it right. But does somebody not understand where some of this stuff came from? That's what I want to focus on right now. So maybe if I divide it by negative 9, it could come out to be, no, even negative 9, no, negative 9 might work to be a bound. So if I do negative 9, two comes down, negative, no it won't, darn it, what was I looking at? Almost. Already I know it's not going to be a bound. Now I can keep going to see if it works, but I'll tell you it doesn't work. Yes?
So for the last one, when we use negative 5, how do we know, like, if we should, go up a scale, like to negative 9, or if we should go down to negative 3?
Oh, right now I was just curious if negative 9 might actually be a lower bound. If negative 5 is not a lower bound, maybe negative 9 is. And if negative 9 is a lower bound, I could throw out 15 and 45, right? Does that make sense?
Yeah.
Or right now you could just go, let me just try 1, negative 1, just because I want a nicer number to look at, right?
A negative bound would just be, ending in 0? Or?
No. It would have the sign changing. So like if this would have been negative, then do you see how the sign is always changing?
Yeah.
That would have been a lower bound. That wasn't negative, so it wasn't a lower bound. Okay. All right, let me move on. So the skills you have to have are, can you create the list? Do you remember what Descartes' rule of signs is? Do you remember how to interpret bounds? So on a problem, I'd give it, just like that one problem on that one worksheet we did, develop the list. Descartes' rule of signs cuts it in half. Divide by this number, and you're supposed to be able to tell, oh, it's a bound. Then you can chop more stuff out of your list. And then the last thing I say will be, factor this fully, find all the zeros. And then you've only got like 3 things left to try, 3 or 4 things left to try, right? Okay. Instead of like 12. Okay. Okay. So, just a quick check-in since it's been a hot minute since we talked about this stuff here. If I do manage to get something factored, can anyone tell me what the x-intercepts are? Yeah, 1, 0. Now somebody else tell me the next one. Negative 3, 0. Now somebody else tell me the last one. Negative. Can't be negative 1. If it was this, it would be negative 1. That's not what it is. So can you see in your head, if you make this equal 0, can you see that subtract 1, divide by 2? It's like a 2-stepper, dude. If you can't, you can write it down. You can write down next to this what makes this 0 and then solve, yes? But maybe you can see this in your head. I would subtract 1, divide by 2, that's negative 1/2, negative 1 over 2. Can anyone tell me what it does at each of these intercepts? What's it do at 1, 0? Bounces. What's it do at negative 3, 0?
Goes
Through? Yes. Why does it do those things? Somebody else tell me. Why does it bounce here? Why would it bounce when it hits that 1, 0? Either like this or it's going to do like that, depending on where it starts. Yes? Why does it bounce here? What's the only difference between this and this and this? Yeah, what other kind of thing does this? Bounces.
Parabola.
A parabola. and what's the power on the x minus 1? Where the 1, 0 came from is the power. What's the power on x minus 1? Second power. And what do we call it? The 2 is the multiplicity. Yes. So the multiplicity is related to the degree of the piece, right? So that piece had a degree of 2. It acts like a parabola at 1, 0. These act like straight lines at their respective zeros, so they're going to go through. Okay. So this is all stuff we've talked about since the last test, right? Multiplicities. If it's already factored, can you find the intercepts? How would you find the y-intercept? Yeah, just set x equal to 0. So we'll get negative 1 squared is 1 times 3 times 1. Woo! So we get 0, 3 is the y-intercept. Okay. Stuff we've done before. Okay. So what I want to do today is somehow related to that thing. Look at that. Just look at it. That's not good. We're going to get into, so we've been analyzing polynomial functions, right? All polynomial functions are combinations of power functions, where the powers are whole numbers. So now we're going to get into rational functions. And again, what kind of a number is a rational number? No. Sort of, but I mean in general. Whole number is a type, but what is a rational number? What's the root word of rational? Ratio. And what kind of number would you call a ratio? Fraction. So rational numbers are any numbers that can be written as fractions. And that's why whole numbers are fractional, because 7 I could put 14 over 2, 7 over 1, I can make it a fraction. Pi, I can't make it a fraction because a fraction is a ratio of whole numbers. I can't do that with pi, right? What the hell is a rational function then? Rational numbers take the nicest numbers, whole numbers, and just put one on top of the other. Rational functions take the nicest functions, polynomials, and put one of them over another. Same kind of idea. So an example of a rational function would be x squared plus 4x minus 7 divided by x cubed plus 5x plus 2. That is a rational function. So what we need to figure out, so can you guys tell, polynomial functions are not that terrible, but the details get a little interesting, but they're going to look like this. They're going to look kind of like Loch Ness Monster. Yes, that's what I always think. Little humps coming out of the sea, right? You guys know with me, out of the waters, do you understand that if I take a polynomial and I divide by another polynomial, the graph of that, does everyone understand the graph could end up looking quite funkadelic? Do you understand? I'm dividing a polynomial by another one, right? That graph is going to look potentially pretty damn freaky. The nice thing though is there are, even though the end result could look freaky as shit, I want to show you things to look for that will tell you what the shape is going to be or where things are going to be. So, I want to start off with the simplest example of this. And you guys are all going to help me. Has everybody got the calculator ready? Okay. You guys going to help? You guys going to get up? You're going to make a graph together? So we're just going to look at 1 over x. So get your calculators ready. What I want to do, let's see, there's 2, 4, 6, 8, 10, 12, 14. And what do I have here? 1, 2, 3, 4, 5, 6. Holy shit. Sorry, I gotta celebrate synchronicities. I have exactly 14 inputs and there's exactly 14 students in here right now. Let me just enjoy that for a moment. All right, so we're ready. I'm gonna assign you a number. So if you don't like your number too bad, do it. Yeah, you get this one, this beautiful, look at that. No, I want you to plug that in, get the output. You're gonna get negative 0.1. You're gonna get negative 0.5, yes? Negative 1. Ronnie, you got negative 2? You got negative, negative 5. Sorry. Yes, Jane. You got negative 10 back there, Trent. And then Dylan, you get positive 0.02. Which way should I go? I'm gonna go this way and then go that way. 0.05, Layla, and then 0.1. And then back here, 0.5. You're gonna be 1. You're gonna be 2, and you're gonna be 5. How did I miss it? Oh, did I get everybody? Did I miss now? 2, 4, 6, 8, 10, 12, 14. 1, 2, 3, 4, 5, 6, 7. Oh, there's 8 up there. Damn it. I'll do 10. So I'll show you what I want you to do. This, I'll be telling you I did this on purpose. So when I plug a 10 in, I get 0.1. So at 10, I'm gonna plot 0.1, which is like right there. I'm gonna make a dot. In fact, the rest of you guys can use blue or purple if you want to. So as you get your output, put that in the table, and then plot the point. Oh, somebody can use this here, and then you can use blue. So fill in your table and then plot the point. Does everybody else understand what's happening? You should all be getting an output. Okay. And then plotting it. Do the best you can with plotting it.
That's about 0.2, right?
What's up? Sorry?
That's about 0.2.
Where are you at? Up there. Yeah, you're good. You're good. What did you get? Did you put it down? Yeah, 0.2? Okay, you're good. You're good. Oh, you're good. There you go. As you get done, look for people behind you that are ready to do their thing. Thank you.
How am I supposed to plot this? Like on this?
Say again?
How am I
What'd you
supposed to
get?
do this? I don't know.
No. So like, just the function is 1 divided by x. And which number are you doing? 0.1.
That's it?
Yeah. So now you fill in the table and then you plot the point as best you can. Wait, let me double check what's happening here. Wait a minute. So which point are you, go for it. Which point are you doing? So that's negative 2, right? So negative 0.05, the output is negative 2, it's down here, right? Okay. There we go. Now we're talking about stuff. Okay. Yeah, so there's 0.1 and 10, yeah. You say 0.1, right? Let's see, 0.05. Oh, I see what happened to purple dude. Whoever did the purple dude, I'll help you out a little bit. It's 0.05, right? So 0.05 is like almost there. And then 50 is 0.02. So it's like almost. You guys see what I mean? Like that's 0.5, 0.1, 0.05. Oh, I see. Okay. I'm looking at this one. 0.05 is right here. That's gonna be 20. 0.02 is 50. Okay, right there. Yeah. Okay. What do you got? Whoa. Are you doing negative 0.02?
Yeah.
Okay. So that should be like off of this a little bit. There. Okay. So can we make some observations? So some of the dots need a little bit of help. It's okay. The scale was weird because I had to make it big and small at the same time. It got a little weird making the scale. Do you guys see what's happening? Like here as I come in. Do you see what's happening as my my inputs approach 0? What's kind of happening? See the function comes in. Look at it. It's coming in and it's getting a little bigger, and then it gets a little bigger, and then a little bigger, and then what's the function do? It just shoots up like crazy. Yes. Yeah. Yes. And that's the sound it makes. Now what happens this way? I mean, it starts getting really down, right? It shoots way up and then it comes way down. I don't know if anyone knows what kind of behavior that is. If I put 100 in, 1 over 100 is stupid small. So it just keeps getting closer and closer to the x-axis. Does anyone know what that's called? If you have something that's getting closer and closer but never gets to it. Let me ask you this. Does everybody agree that here, let me get this on for everybody who's somewhere, search party being sent. Does everyone agree that, how do I make a fraction 0? What's the only way for a fraction to be 0? If the numerator is 0. What is the numerator of this function always, no matter what we make x? What's the top?
1.
Top is 1. You guys with me? Right there, we know that the output cannot be 0. Yes? I need you.
Yes.
Some of you guys are looking my direction, but you're not really listening to what's going on. So, like, the top can never change. It's always 1. But as the bottom gets bigger and bigger and bigger, what kind of number is that? What kind of number is that? It's freaking small. Yes? That's a small freaking number. So the bigger my inputs get, the smaller my outputs get, but they never get to 0. Does anyone know what that's called? Starts with an A.
Yeah.
Asymptote. One of my favorite words is asymptotic behavior. Yes. So asymptotic means it just gets really close and never gets there. I'm just going to keep touching my own arm up here for some reason. Okay. Is everybody with me? Sort of? Has anyone, pretty sure that you've never heard the word asymptote before? Have you all heard the word asymptote? Okay. I was really bummed out. I have a shirt with Gandalf standing on the x-axis, and he's got his stat. He says, "You shall not pass." So that's an asymptote. Like, look here. Does this ever get to the y-axis? In order for the y-axis, how do I find the y-intercept? I make x0. If we try to make x0, what happens? If you try to put a 0 in for x, what happens? I like it. Some in the back went bad things. What? If you try to divide by 0, what do you call that? Undefined. Now we're going to make it a little more precise. Undefined is immediately correct because there's no number defined to be the result of divided by 0. But do you see what happens though? It actually goes to infinity. It just shoots to infinity. 1 divided by 0.1 is 1 divided by 1/10 is 10. 1 divided by 0.01 is 1 divided by 1/100th is 100. Because how do you divide by fractions? You multiply it by the reciprocal, yes? So as I keep putting smaller and smaller x's in, just like you guys discovered, the outputs just shoot up. Okay. What happens on the other side? All the same shit, just on the other side, yes? So here we've got, yeah, somebody put the negatives down, I like it. So, I didn't do negative 10 today. I should have done negative. So that's negative, sorry?
Negative 0.1.
Yes, thank you. So it's right up here. Oh, you got it. Okay, I got you. So it's coming over, down, and then it just shoots down. So that one's a little bit wonkier. It's okay. We'll be fine. Okay. Same picture, just kind of like on the other side. Why is it negative? Because my inputs are negative now. Yes? So of course my outputs are negative. Same idea, just negative. It's like this one flipped, yes? Can we stop for a minute? I love you guys. Okay. This is trippy. So there are two different types of asymptotes here. There's a vertical asymptote here. So it cannot hit the y-axis. That's a vertical asymptote. In fact, what would you say the domain of this function is? What's not in the domain of that function? What's the only number not in its domain? 0. Vertical asymptotes are literally walls I put on the x values you're not allowed to use. That's my way of saying you cannot go here. Yes? That's why I got a little Gandalf going, you shall not pass. So my function is like, holy shit! You know, it's like, I don't want to go there because black holes happen and you can't divide by 0. Okay. In my head, I always have the, it's a trap, and they have to pull up because those shields are in right here. Okay. Sorry, some of you guys are with me. Okay. So, this is a very simple, this is the most simple rational function, 1 over x. They're going to get trippier, of course. So now we're going to broaden our discussion. When they get trippier, how do I discover the vertical asymptotes versus the, you're not going to believe what we call this one. This is a horizontal asymptote. We are very creative people, math people. Horizontal asymptote, because it's horizontal. It's crazy. Why do you think it has a horizontal asymptote? Because if I divide by bigger and bigger numbers, my output gets smaller and smaller, but it never gets to 0. That's the whole idea of an asymptote. You get closer and closer, but you never get there. That's an asymptote. Okay. And I want to say this. I'm going to introduce, have I already shown you this notation? I don't think I have. No? So the limit of a function as it approaches an input. There's an N in there, Jeff. So the limit as x approaches 0 of f of x from the right. So that little plus sign. So I'm going to push my luck here. I'm going to show you some full notation. This is full calculus notation. But the idea is very straightforward. Can you guys remind me, as we approached, as I put numbers in to the right of 0, as we got closer to 0 from the right, what were my outputs doing? In fact, they go up forever. So the limit, we would say, is positive infinity. Now what about the limit as x goes to 0? Jeff, you can do it, buddy. From the left. Now it's, as I put numbers from the left, what are the outputs doing? They are going down to negative infinity. What's the limit as x goes to infinity of the function? As I put bigger and bigger numbers in, what are my outputs doing? Getting very close to small. And what's 0? So they're getting really close to 0, yes? Just like this. If I put more and more zeros on, isn't the result getting closer and closer to 0? Okay, is everybody with me? Love you guys. And of course, just to complete this, the limit as x goes to negative infinity is just this way. And of course, the same thing happens, just it comes from the other side, but it's still going to 0. Yes? So we have a vertical asymptote is a wall we put that says, you cannot go here. The horizontal asymptote, we're going to learn that it's not as strict. It just says, it's kind of like end behavior. Where did the horizontal asymptote come from, letting x get really big, yes? So that's end behavior. So the horizontal one says, hey man, hey, so sometime can you get close to me? That's what the horizontal asymptote says. This says, you cannot be here. This says, hey man, hey, can you get close to me at some point? So it's not as strict of a wall. Okay. So, Now that we got some ideas, you saw one reason I want to do this is you guys helped me create it. You guys did some of the work that went into it, but it's a concrete example of why asymptotes exist, right? We see them happen. They just happened. We saw them come out of this, so we know they exist. So now I want to talk about, what if I give you a funkier function? How can you tell where the vertical asymptotes are? How can you tell what the horizontal asymptote is? All that kind of business. That's the next thing I want to do. And you're all like, well, you're in charge, man. Do it. All right. And I apologize. Today's going to be a lot of talking, so too bad. So rational functions. Let's start with vertical asymptotes. So vertical asymptotes are the real walls. They're the one you cannot go cross it, because then you've done something illegal. I might get into one little thing at the end, but let me start off with some standard kind of stuff. There. So let's take one step up from where we just were. That'll work. Okay. So this one had a vertical asymptote at 0 because 0 is not in its domain. So how do I figure out how many and where the vertical asymptotes are for this guy? Why can't we not see it? Can you see what values make the bottom 0 easy? No, the answer is no. What do I do so I can see what makes this 0 easy? What can I do with this? Factor. How do I factor this thing? -7 plus 3. So what are my vertical asymptotes? What do I have to tell the function, hey, you can't go here? Where are my vertical asymptotes? So here, let me do this 2 steps. What's the domain of this? X can't be what?
7.
Can't be 7, because that would make the bottom 0. Can't be -3. Is everybody cool with that? That's the answer to the domain question. If I say, where are the vertical asymptotes? There's one at x equals 7, and there's one at, get out of there, y. There's one at x equal -3. So the domain is saying, what x's are you allowed to use? Vertical asymptotes are saying, where do you have to put the wall? Because you can't use those things. So I'm going to put a wall at 7 because I can't use it. I'm going to put a wall at -3 because I can't use it. Okay. Now, eventually we'll do the next step. But so at 7, my function could do this, like that one did. Yes, it could do this. It could do this. It could do this. It could do this, right? It just has to slam up against it somehow. Now we're going to do the work that shows us kind of like which thing it's doing, but I know it can only be one of those things. It's got to slam up against it, yes? Because it can't go through it. Okay, maybe. Oh my God, just like that. That was the chairs, my vertical asymptote. So what about, that's a very math joke. Yeah. All right, let me give it a little twist because there's not much to this. But let me see if you guys are cool with what I'm about to do. There's something about this. Now you can factor the bottom, correct? Go ahead and also factor the top. See what happens. So how do you factor the top?
Greatest common factor.
Yeah, 4 comes out. And how do you factor the bottom? The bottom is nice. You'll get a little nice too. Yeah. Now, if you just look at that, it looks like there's 2 vertical asymptotes, yes? I wouldn't blame you for thinking that, but you would be wrong. Here's the problem. Why does a vertical asymptote exist? Because there's something on the bottom that goes to 0. So if I divide by very, very tiny numbers, my output gets very, very big positive or very big negative. Does that make sense? But in this case, as I get close to -1, do you agree this gets tiny? Like if I put negative 0.9 plus 1 is negative, it is 0.1, it gets tiny. If I put negative 0.99, that's 0.01, yes? But isn't this also? So the bottom is getting tiny, but so is the top. That's the difference here. So those 2 do cancel, but the domain doesn't change. Okay, I really want this to make sense. What's the domain? What numbers can I not use?
1, -1.
Yeah, I cannot use 1, and I cannot use -1. Because if this number is anything except 0, I can cancel it. 0 divided by 0. What is 0 divided by 0? What's 0 divided by anything? Almost. 0. What's anything divided by 0? Undefined. Yes? Infinite. So 0 divided by 0 is somehow both 0 and infinity at the same time. Okay. So as long as this is not 0, so I can't let x be -1. As long as it's not 0, it cancels, correct? Any number divided by itself is 1 except for 0. 0 divided by 0 is freaky. Maybe. So the domain says I can't use these. But what is my only vertical asymptote? 1. Now, a great question right now should be, then what the shit is happening in -1? Right? It's a great question for you to have, because at 1, there's going to be a wall, and I'm going to slam up against it like we did here, yes? Something weird still has to happen in -1. I'm not allowed to use it. So let me ask you this. Does everyone agree that this function equals this function almost everywhere? Do you understand that when you factor and cancel, it's still the same? If you reduce 6/8, did you change it? No, it's still 0.75. It just looks different, yes? These functions are the same everywhere except -1, yes? But if you put a -1 into here, what do you get? What do you get when you plug a -1 into here? What's -1 minus 1? What's 4 divided by -2? -2. Good. I like it. You're like, I already told you. So, let me show you. This is too cool. You're like, we'll be the judge of that. I understand. If I put this in my calculator, Jeff, not 19. No, not 18. Okay. Let me make a normals window. So, do you guys see? In fact, let me even make this better. Let me zoom in at least. I don't know how to do the other thing I was just thinking about. Do you guys see how there's a wall here?
Yeah.
Right at 1, yes? You guys see that? Now, at -1, does everything look cool? It looks like it's fine, doesn't it? So, have I shown you guys, if you hit second trace value, you can tell it what's the value at 0, and it will tell you the output at 0, yes? Do you see that? So if I ask it, what is the output at -1? You guys ready? Watch what it tells me. What did it say? Nothing. There's an open circle there. Where exactly is the open circle? It's at -1, what did we say? Didn't we calculate it? Yeah, negative 1, it should be at negative 1, negative 2. Why is that? Oh, yeah, I'm looking on the wrong side. Negative 1, negative 2, roughly. If I do a trace, do you see how negative 1 is close to negative 2? Do you guys see that? So there's an open circle at negative 1, negative 2, because I'm still not allowed to use negative 1 as an input. But there's not a wall there because it canceled with the top. So what goes there instead is this open circle. It says, nope, there's no output here. You're not allowed to use that input. So this is the first time I think you guys have seen what it looks like when there's an open circle in the wild. I've given you graphs with open circles in them, but here's a function that has an open circle in it. And why doesn't it show up? Because the open circle is 1 pixel big, so you can't see it. You with me? Maybe. Okay. So how do I find vertical asymptotes? Where do vertical asymptotes come from? I'll accept a few different ways to say it.
0 to the denominator.
Beautifully, you said it both ways in one. It comes from the denominator, whatever makes the denominator 0, and another way to say it is it comes from those things that are not in the domain. I like it. Oh, do you have to head out? If you have to head out, grab one of these before you go. I don't know if you're packing up. Okay. So on this problem, we did already, but we saw there at 1 there was a vertical asymptote, and the function slammed up against it. Okay. Pretty sure I warned you today it was going to be me talking a lot. Horizontal asymptotes. So we saw one up here on the board. We saw a horizontal asymptote here. And it came from letting the inputs get really big. Really big positive, really big negative. Yes? That's they're a type of end behavior. Remember when I said end behavior, it might be this, but in the middle it could do all this kind of wobbly shit. That's the whole idea, right? Could be this, but in the middle it could be whatever it wants to be. Same thing here. Horizontal asymptotes are end behavior. What does it have to be approaching at the end? There's 3 situations that we get into with horizontal asymptotes. One situation I have up on the board. So let me give you a more interesting example of it. So somebody remind me what I just said. Where do horizontal asymptotes come from? When we...
Take the denominator.
No, that's vertical asymptotes. They come from what's down the domain. Where do horizontal asymptotes? When I let the input get... When I let the input get... What happens to the x's if I go way out that way? What happens to the values? If I go way out that way, what happens to the values? They get really small. No, not the outputs. What happens to the x's? If I kept going, what happens to the x's? They get bigger, yes? 10, 11, 12, 100, 1,000,000. Right? And of course, if we go the other way, they just do the same thing. Just get bigger with it, yes? So horizontal asymptotes come from letting the input get really big. In this rational function, what is the degree of the top? What's the degree of the top?
2.
Sorry.
2.
2, yes. And what's the, second degree. What's the degree of the bottom? 3rd degree. I like it. So ready with me? Which one of those is going to grow faster when I let x get bigger and bigger?
The bottom.
The bottom, of course, right? 5 squared is 25, 5 cubed is 125, right? So if the bottom is getting bigger faster, what's happening to the output of the whole thing? If the thing I'm dividing by is getting bigger faster, what are my outputs doing? Getting small. Does that make sense? So like if x is 5, this is like 25 minus 3. This is 125. If x is 10, this is 100. This is 1,000. Do you see what I'm saying? That division is getting smaller and smaller because the bottom is getting bigger and bigger. The top can't keep up. So the whole thing goes to 0. So this is a really simple example. Is the degree of the bottom bigger than the degree of the top? Yeah. Does anyone know what the top degree is here? Here we go. How many x's do you see on the top?
0.
So the top is 0th degree, and the bottom is 1st degree. So the bottom is bigger. It's going to grow faster. One doesn't grow at all, so that's very in your face. I'm just dividing by bigger. I'm going to go to 0. So anytime, this is so cool, anytime the bottom degree is higher than the top, the horizontal asymptote is going to be y equals 0, otherwise known as the x-axis. Anytime the bottom degree is higher than the top. So what if I have a situation where the degrees are the same? Do you guys see that these degrees are the same? They both have a highest power of 3, they have a 3rd degree. Yes? So that means neither one is growing faster than the other one, but they do have a relationship between each other. So let me show you the technical way to get this, and then I'll tell you about the shortcut. Just to remind you guys, how do I investigate horizontal asymptotes? I let my input get really big. Just like we did up here, we let our input get bigger and bigger so we can kind of see what it's doing. So this is a little bit of a trick that we can do. What number can I not divide by? 0. Okay. And if I'm letting x, so this again, this symbol means the what are the outputs approaching as my inputs get big. That's kind of like the way to read that. The limit is just the idea of what the outputs are. They approaching something. If I'm letting x get really big, could x be 0? You guys with me? If I'm letting x get really big, could x be 0? No. So am I allowed to divide by x if x can't be 0? Yes, okay, good. So you gotta be really careful. In general, you can't divide by x because x could be 0. Okay. You can see that function we divided by x and part of it went insane. So here, I'm gonna divide by x cubed. You'll see why here in a minute. What's x cubed divided by x cubed? What's x cubed divided by x cubed? What's something divided by itself? 1. What is x squared divided by x cubed? Let me write this out so it looks a little bit easier to see. I'm just going to divide everybody by x cubed, right? What happens here? How many x's cancel? 2. How many are left?
1.
Where?
In the
Good. The exact same thing happens here, except they only lose 1 x, so there's 2 left on the bottom. Now, help me out. Here's why we did this. If x gets really big, what happens to 4 divided by x? 4 divided by really big gets really small. So in the limit, as x gets as big as possible, what does that become? What does that approach? 0. Same way our 1 over x approach 0. Same thing here, right? 7 divided by even bigger is going to go to 0 faster. 5 divided by really big gets really small. 11 divided by really good big is really small. So what's the only thing left? All this went to 0, yes? So what's left? 1/2. Yes? 1 over 2. That's the horizontal asymptote. Y equals 1/2 is the horizontal asymptote.
It's approaching 1/2.
Do it again.
It's approaching 1/2.
Yes. So it could either be coming down and there's going to be a dotted line and it's going to approach 1/2 from there, or it could be coming up from below and it's going to approach 1/2 from below. So what's the shortcut? If I lost $11, I'm a teacher, so that would affect me to some degree, yes? Don't have a ton of money. So $11, I'm gonna find it, I'm gonna go get it. If I am Bill Gates or whoever you want to insert, Jeff Bezos, if I'm the other Jeff Bezos, there's only one Jeff, and I lose $11, am I gonna scramble to get it? Am I gonna like get on my knees and look around? Or am I just gonna be like, I'll do that, yes. And yes, I do contribute to Jeff Bezos. I hate that I do, but I do. I buy stuff from him. It's like, damn it. All right. So when X gets really freaking big, this is nothing, yes? If X is a billion, take 11 away from a billion. I'm like, I don't care. What do you mean? You with me? Now, think about this. If X is a billion, do you all agree 5 times a billion is big? What about 2 times a billion cubed? That is insane. So this is nothing compared to him. So every single one of these terms, when I compare it to these two, don't mean shit. And what does that reduce to be? 1/2. So the shortcut, the ultimate shortcut is just, if the degrees are the same, the horizontal asymptote is the ratio of the leading coefficients. What's in front of the cube term 1? What's in front of the cube term 2? 1/2 is the horizontal asymptote. Will that become useful in calculus? Maybe even Calc 2? Hell yeah. I keep reviewing this because my Calc students forgot it or whatever. So it's better to know it going in. Okay. So I got one situation, bottom degree higher, the whole thing goes to 0. If the degrees are the same, it's the ratio of the leading coefficients. So let's do one more example of that. Yeah, exactly. Jeff's got to be an asshole sometime. So, the highest powers are what? On top of? No, what's the highest power? Yeah, what's the highest power? It's 3. Third power, yes? And then, so what are the leading coefficients on the top and the bottom? The number in front of the highest power is 4, and the number in front of the highest power is -6. So what's my horizontal asymptote? 4 over -6, -2/3. So at y equals -2/3, there would be a horizontal asymptote. So before I do the last, no, I don't want to do the last one. I want to do one example problem and then we'll head out. So I've got this here. I want to do this one. A nice colorful thing here. Okay, so let's do this mostly together here. Let's see. Can anyone tell me the y-intercept for this guy? overthink it. You always find it the exact same way.
1/2.
Yeah. How do you find the y-intercept? You make x 0. So you can literally just cover everything that has an x in it. You reduce that, it's 1/2. So 0, 1/2. Now what do you think a really good idea, before I answer any more questions, what's a really good idea?
Factor.
Yeah, pretty much factor, so I can see all my parts, right? How do I factor the top?
You got a 3.
So I can take a 3 out first. On the bottom, I need the right numbers.
X plus 1.
Yeah, x plus 3, x minus 2. And then what's one more thing I can do on the top?
Factor x squared minus 1.
Yeah. So can somebody tell me the x-intercepts? And I'll tell you the biggest mistake I see people make. How do you find the x-intercepts? You make what? y0, which means make the output 0.
So set equals 0.
Sure. How do you make a fraction 0? The numerator 0. So the biggest mistake I see is people give me 4 x-intercepts. No. -1 and 1 make it 0, yes? What does 2 and -3 do?
Makes it not exist.
Makes it freak out. Poor little thing, yes? Those are going to relate to my what? 2 and -3. Those are going to become my... Are those in my domain? 2 and -3, are they in the domain? I'm not allowed to use them, so what am I going to put there? Walls! Yes, so they're going to lead to my vertical asymptotes. Yes, vertical asymptotes come from the idea behind what goes in the domain. So you got to be really careful. X-intercepts make the top 0. Vertical asymptotes make the bottom 0. Yes? What would make the function freak out? Where do we have to build our walls? X equals -3. X equals 2. Now don't say anything out loud. Think to yourself, what situation are we in for the horizontal asymptotes? And I did the best I could. It gets really weird trying to describe generally. But do you guys see how n is the highest power, m is the highest power, top and bottom?
3/1.
If the power on the top is smaller than the bottom, it goes to 0, just like we talked about earlier. If the top grows faster, it goes to 0. If they're the equal degrees, then it's the ratio of the leading coefficients. And then this situation we'll talk about probably next time, but we'll come back to this one. This gets a little weird. Slant asymptote. So what situation are we in for this horizontal asymptote?
Equal.
Yeah, equal degrees. So what is the horizontal asymptote?
3.
Y equals 3. Say it. Yep, 3/1. Mm-hmm. That's the leading coefficients, yes? Okay, I like it. Now, the way I do this, I know you have calculators. I know this. But the way I do this, so you can plug this in your calculator. I always use the factored form because it's just easier to do by hand. F of -4 would be 3, -4 plus 1, -4 minus 1, over -4 plus 3, -4 minus 2. So I just plug a -4 in. And where did this number come from? You'll see in a minute. So I haven't shown you how to figure out how to get these yourselves. -3 divided by -6 is 1/2. So I get -15, so the negatives cancel. I get 15/2 is 7.5. Is that okay? 15 divided by 2. And then f of 3 would be 3 times 4, right? 3 times 4 times 2 over 6 times 1. 3 times 2 is 6, so f of 3 is 4. You are the real MVP, f of 3. Okay, I like it. How you guys doing? You guys, this is, I love it. I love it. Nobody's sleeping. I love it. It's good. Because this stuff gets a little boring, I understand. The key thing is the scale on the y-axis. So a lot of people just don't pay enough attention. What is my biggest y-related number? And just to help you guys out, what point did we find here? What points are these two? What point is this one? Input, output. And then input, output. So what is the biggest y-related value? 7.5. So I want to make a scale where 7.5 has a place to be. Poor little dude. So what scale should I use on the y-axis? Don't want to use by ones, correct?
You do by 2.
2s. That's great. So I'm going to do 2, 4, 6, 8, 10. Negative 2, negative. And the x-axis, all my x-related values are less than 4, right? Oh, well, there you go. Negative 4 is the most extreme. So I'm going to go by ones on the x-axis. So now you can plot your stuff. Let's see. I can put my walls up. Let's go step by step. My y-intercept is 0, 1/2. X-intercepts are negative 1, 0, 1, 0. My walls are at negative 3. My vertical walls are at negative 3 and 2. And my horizontal wall is at 3, which is right between 2 and 4. Okay. Oh, almost forgot. Okay. There's a skill here that we sort of have to focus on by itself. Does anyone see how I've broken this up into 3 regions? There's a region here, there's a region here, and there's a region here. In this region, it's got to slam up against that wall. It could either do it up here or it could do it down there. And then it's also got to slam up against that wall. How do I know it doesn't do this? It can only do this or this. How do I know it doesn't do this?
You have negative 4.
Yeah, right now, I forgot I have other points. But even before I did that, is there any x-intercept here?
No.
So there's no way for it to get through the x-axis, yes?
Yeah.
It can only go through the x-axis here. But you're right, I do have this point here, negative 4, 7.5, which is about right there. So then I know it's got to, what I desperately need you guys to get, and I need to focus on, and I have not left myself enough time, is there's only so many things this could do. It's got to be a function, so it can't be here and here, because then it wouldn't pass the vertical line test, yes? It could only be here, and we know that's where it is, because I see the point right there. So it slams up against this wall, and it slams up against that wall. See that? Or it could have been here, if there would have been an x-intercept there. Look up here. What other point did I tell you? Now you see why I told you to do the points I did. Because right now it could be either here or there, but of course f of 3 is 4, so it's got to be here. And then the middle is where things get wonky sometimes. The middle could be like a cubish, it could be a parabola this way, parabola that way, it could be a cubish the other way. There's one little thing that helps us out. What are the multiplicities on the x-intercepts?
1.
So if the multiplicity is 1, what's it got to do there? It's got to go through. So the only way I can hit this y-intercept and go through is to do this. Look almost parabolic. It is not a parabola, but it does look parabolic, yes? So it's got to hit the y-intercept and it's got to go through those x-intercepts. So it's got to look like that. So once you establish your walls and you plot the points, it's very limited into where it could possibly be. Every wall you got to like slam up against. Now what we're going to talk about tomorrow is I want to solidify that idea of what it could look like in regions, because every one of these looks different, which is neat. And there was another thing that I will do tomorrow that I currently forgot what it is. Okay. And then, of course, we established the quizzes earlier, right? Yes, I did announce the quizzes. Yes. Yes, we have one this Thursday and one next Wednesday. Cool. All right. All right, guys. Go somewhere. Decompress. I'll see y'all tomorrow. Maybe more people.